Welcome to the demonstration for the generic Arduino-based thermoelectric cooler regulator, or GATECeR for short. Team members include Ryan Kahn, David Thompson, and Ann Vo. This project is using an Arduino Nano EVRY unit to control an Adafruit thermoelectric cooler assembly module. That module includes a tech, a heatsink, and a fan, which look to use 60 watts of power to chill the cold plate. The Arduino Nano is connected to a pot that allows us to enter a set temperature point. It's connected to a MOSFET control board that helps separate the 12 volt 5 amp power supply from the rest of the components and keep them from melting. If we had a second MOSFET control board, we'd control the fan separately as well, but as is, it's connected to the 12 volt power supply at all times. To monitor the temperature, we're using a TMP36 sensor and the simple expedient of a metal screw nut to help maintain the connection and keep ambient air from affecting the temperature readings. The entire board is running off of its own 5 volt power supply, which with an on-off switch allows us to enable the ULCD screen that displays data throughout the operation. The Arduino Nano itself could be controlled untethered from the PC with connecting the 5 volt power supply to the V-in. However, we are using the PC for the Arduino IDE serial plotter. So we'll get things connected and started. And the first thing that will happen is the ULCD will initialize. It will reset and then unreset. And then start running a control loop that weights the readings from the temperature sensor for a better reading. We run that 800 times, and as you can see, output to the ULCD screen while we're doing that. And then the temperatures are shown on the LCD screen once we're in the operation phase. So in this case, we can see that the pot sensor has got us connected at about 11 degrees Celsius. We are running a temperature sensor about 13. In Fahrenheit, that would be about 55, as you can see, and it is dropping. The Arduino then controls the MOSFET to output pulse width modulation power. So right now it's at full power because it has a range of 0 to 255. I'll cut over to the serial plotter, where you can see the red line is our set point, right there a little bit below 12, and the orange line is the temperature. So it has already come down, and as it has gotten a little bit underneath where we're trying to get, now the PID software control is changing the pulse width management to end up dropping the amount of power run to the tech there. And so it doesn't actually need as much power to keep it as cold. And as it runs, this line will end up coming back up. Now I'm going to pause here for just a moment and let it catch back up for a moment and then show off a little more. And we're back. As you can see, after a quick drop in temperature, it took a little bit for the proportional integral derivative PID to end up getting that matched up, but it is fairly close in temperature and holding fairly well. The PWM values keep jumping, but it's in minor amounts. So we will adjust the control and drop the temperature a little bit. You can watch then how that changes on the plot. As the PWM values kick up to full, they're up to 255 again, and the temperature is fast dropping down to the new set point. I'm going to pause it once more here. And we're back again. As you can see, we handled the temperature drop of several degrees down to about 7.5, and the plot shows that we've fairly well stabilized, and the PWM values running are a little bit different now. I'll do one more change on the pot to go back up just a bit, and pause again and come back and show what the graph does at that point. It is slower going back up because we're requiring it to warm back up, which is ambient. And with that, we will pause for just a moment. And once more, we're back. You can see we've gone back up to the temperature change to around 8.8 degrees Celsius, and everything is holding fairly well. So, thank you very much for watching our demonstration, and hope everyone is doing very well.